Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. So as the title of the talk indicates, this topic is very much a work in progress. So while I think you'll hear some nice results, there's interesting challenge to find to understand the generalizations. Anyway, happy to have Balu talk about the toward optimal algorithms for prediction.
Okay, so thanks, Yuval. This is joint work with Nick Gravin and Yuval Perez, and Nick is a postdoc in Microsoft Research at New England. He visited us for a few weeks this summer. Okay, so this talk is about prediction with expert advice, and this is basically a classical sequential decision-making process. And we're going to study this problem in a purely adversarial setting. There's nothing stochastic here, except for the strategies of the algorithm or the player and the adversary. Okay, so the setting is very simple. Here's how the game proceeds. So there is a player, and at each time step till the game stops, some stopping time, the player has to make a decision. And for making this decision, he has k experts at his disposal. Each of the experts at the beginning of the day ask him to do something, and he has to follow one of these experts. And after he does that, there is an adversary who comes and sets a gain. Okay, so if you follow expert I, then the expert I gets gain GIT, and the player, if he uses expert I, he'll get the same gain as the expert. Okay, so the player chooses expert J, he gets GJT, and after day T, he gets to see the gain of all the experts. Okay, so is the setting clear? When day T begins, the player gets to see the entire history of gains, but not the gains on day T. And using these things, he has to pick which expert to follow. After this, the gains are revealed. Okay, so this is purely adversarial, and I'm not going to assume anything about how the GITs are related, except that they're all bounded in 0 to 1. Okay.
Does the adversary know what the player picked when he sets the gain for the experts?
Well, the adversary will know the player's strategy. We are going to do minimax, but
he doesn't know what he picked.
Yes, but I mean, if you knew what he picked, then
no, because the way you wrote it looks like the player picks and then the adversary.
Okay, yeah. So I'll make it clear. We're going to talk about the minimax. Yes. Okay. So there are two well-studied variants. One is that the stopping time is finite, equal to some capital T. The other is that the stopping time is a geometric random variable with mean 1 over delta. Both of these are natural, and we'll study both of them. Let's talk. Okay, so what is the strategy? What are the strategies of the adversary and the player? So at time step T, if you were to make a decision, you have at your disposal the gains of all the previous days till T. And I'm going to call capital G, use capital G for the cumulative gain over all the past days. So what is the adversary strategy? The adversary strategy is basically a distribution, which is a function of all these gains in the past days, using which it will draw the gain vector for day T. And basically basically adversaries are most powerful. I won't prove this, that you can restrict the gains to be 0 or 1. And what is the algorithm strategy? It has to pick a probability distribution, day T, over the k experts, which is again a function of all the gains over the past days. I'm going to use AT for the algorithm's reward at time T. And what's the measure? What do you want to measure here? What does the algorithm want to minimize? It wants to minimize the regret, which is the difference between how the best expert did, okay, max over all I of the cumulative gain of expert I, minus what the algorithm got, which is the sum over all the days of what it got. Okay, so what is the worst case regret? If you fix the algorithm A, what is the worst regret possible? You maximize over all the distributions of the regret you get for distribution T. So what's the worst case optimal algorithm's regret? So you choose the best algorithm, assuming that the adversary is going to be tailored to kill this algorithm, right? This is the minimax optimal regret. Then we'll use the minimax theorem all over. you can switch the order of the adversary and the algorithm. That is, if the player goes first and the adversary is designed to kill the player, it's the same as adversary going first and the algorithm designed to kill the adversary. Okay. So these two result in the same regret, the regret of the game. Okay. So I have to go through this mandatory motivation slide. This is really the first framework proposed for online learning. There's special significance because of that. There's applications all over the place. If you didn't know the standard application, the weather predictions and asset predictions, click predictions. Okay, so what is known for this problem is the beautiful multiplicative weights algorithm, which works as follows. If you have cumulative gains at day t minus 1, g1 to gk, for the k experts, then you compute the exponentials of all these cumulative gains and decide to follow expert I with probability proportional to this exponential of the gain. Okay, so there is a parameter eta which can be tuned, and for the optimal value of the parameter, this multiplicative weight algorithm gets a regret of square root t log k by 2. T is again the time horizon and k is the number of experts. So beautiful thing about this algorithm is it does not reference the number of remaining time steps or the total number of time steps t. It also does not reference the past predictions. All it does is use the cumulative gains. And this is asymptotically optimal, doubly asymptotically optimal, as both the time horizon and the number of experts goes to infinity. Okay, so if this is there, what do we want to do here? So all along, the optimal algorithm and the lower bounds have been two separate streams of work, the algorithm and the lower bounds, and this has resulted in a gap between the upper bound and the lower bounds. What we really want to do is simultaneously develop the optimal algorithm and the adversary to completely bridge the gap between upper and lower bounds. Okay, so basically we want the optimal algorithm and the adversary, but not just that. If the algorithm is hideously complicated, then there's no point. Okay, is there an algorithm which is as simple and intuitive as the multiplicative weights algorithm, but is also optimal for a small number of experts, not just asymptotically? Okay, so that's really the question we'll be studying.
So was there any complex algorithm already?
Is that?
Was there any complex algorithm already?
No. There is the multiplicative weights algorithm. I mean, if you design some complex algorithm, then you have to justify the small gains versus the complexity you get. Okay, so here are our results. I'll begin with two experts. Okay, so the optimal adversary is the following. It's a very simple optimal adversary. So you set the gain of the experts always disagree, basically. You set expert 1 to the gain of expert 1 to 1 and 2 to 0 with probability half, or expert 2 to 1 and expert 1 to 0 with probability half. Okay, so they perennially disagree. And this is the precisely optimal adversary, not just asymptotically. And the optimal regret that you get in the finite horizon model is exactly equal to the half the expected absolute distance traveled by a simple random walk in t steps. Again, this is exact, not asymptotic, but as t tends to infinity, this quantity is square root t over 2 pi. Okay. Now, if you compare this to what the multiplicative weight algorithm gets, the regret of the multiplicative algorithm, the multiplicative algorithm regret is 47.5% larger than this. Okay. And similarly for the geometric horizon model, this is the exact regret, okay, where delta is the probability with which the game will stop today, and therefore the expected time for which the game will last is 1 over delta. So this is the optimal regret, and as delta goes to 0, optimal regret is this number. Okay.
What was geometric horizon?
Geometric horizon model is that the stopping time is not fixed. The game could end any day with probability delta. Okay, so this is the optimal regret and the optimal adversary, and here is the optimal algorithm, okay, for two experts. So what is the numbering convention? The numbering convention I use is I'm going to number experts in the descending order of cumulative gains. Okay, the experts 1 and 2 do not refer to the identities of the experts. It refers to the leading expert in terms of gains and the lagging expert. So the algorithm is extremely simple, okay, as simple, perhaps even simpler than the multiplicative weights algorithm. So you initialize psi to be some function of delta. This is basically roots of the characteristic polynomial of a recurrence we'll set up later, but for now it's just some function of delta. Okay, as delta goes to 0, it's basically 1 minus square root 2 delta. Okay, you set this, and for each time step t till the game stops, you do the following. You compute the cumulative gains for the two experts, right, G1 and G2 of t minus 1, you compute the difference, the cumulative gains, okay. You choose the lagging expert with probability half of psi to the t, and with the remaining probability mass, you choose the leading expert, okay. And this is the precisely optimal algorithm for every delta, not just asymptotically, okay. Okay, so this algorithm is not multiplicative weights algorithm, but is a novel twist on multiplicative weights. So if you think about it, it's really multiplicative weights on the lagging expert, right? So you're doing multiplicative weights on just the lagging expert here. The remaining probability mass is being used for the leading expert. In comparison, the actual multiplicative weights is this, okay? And our algorithm, optimal algorithm, cannot be expressed as a multiplicative weights algorithm or even as a convex combination of multiplicative weights algorithms. So it's outside the MWA family. Okay. Okay. So that's it for two experts. So we got the optimal adversary, optimal regret, and the optimal algorithm.
What's the algorithm for the finite horizon?
The algorithm for finite horizon will depend on the number of remaining time steps t, so it will get complicated because there is going to be an inevitable dependence on the number of, therefore it's not succinct, cannot be succinctly described like this, right? Because I'm describing this for every delta, and if you want it for every t, surely, for instance, you know, if you know that.
Okay, so the maximum distribution is going to be uniform.
Yes, the adversary strategy is the same for both the finite horizon model and the geometric model. It is going to be half and a half.
In the two experts case.
Yes.
For two experts, yes.
Is there a simple way to see that that's the optimal adversary other than it being?
I'm going to do all those things. Yeah, I'm going to derive the optimal adversary and the algorithm. So this is just stating the results.
So the lower bound for the two expert finite horizon is the same as the one for two constant experts. The asymptotic minimax value. You know, when you have two constant experts, 0, 0, 0, 0, 1, 1, 1, you get the same asymptotic value.
Okay.
And that's exactly because your maximum distribution is oblivious. Okay.
Oblivious of.
Because it's just half, 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 half. It's oblivious to what to the strategy. You say generally the adversary will depend on past realization of gain and losses.
Yes, this is history independent. Yeah.
In this case, it's not.
Yes.
And so this also applies to the model in which you have a static experts. So the experts are just constant, and they give always they get the same prediction. This is an older result by Culver. That when he gives this,
Static experts.
the setting is different. Okay?
Yes.
It's because the experts are constant,
Right.
and you know that. So you're not, the adversary is not maximizing over the prediction of the experts, but to just showing that this is not
Right.
giving any extra power.
Right.
You already get that right.
Right. Yeah. But for 3, it'll become different. Yeah. Okay. So that's the story for 2 experts. So here's what we prove for 3 experts. I'm saying 2 and 3 differently because 3 is significantly more complicated than 2. The optimal regret, the geometric model, is precisely this for every delta, not just as delta goes to 0, but as delta goes to 0, this number is 2/3 of square root 1 over 2 delta. So in comparison to 2, the constant was 1 over 2 here, half, it becomes 2 over 3, and the multiplicative weight algorithm's regret is 39.3% larger. Okay. And the optimal adversary in the geometric horizon model as delta goes to 0. So here I'm going to describe the asymptotic optimal adversary, but even the absolutely optimal adversary for every delta is simple. Okay, so note that a priori it is not even clear that the adversary should lend itself to a succinct and small description. It could be very complicated, but it turns out that the optimal adversary is simple. Okay, so you advance experts 1 and 3, the leading and the lagging experts together with probability half, and the middle expert with probability half separately. Okay, so this is the asymptotically optimal adversary, and if you want the exact optimal adversary, you have to do something slightly different at the boundary point. At the origin, you have to do something different. But
maybe you can just write this like the 2 vectors you can give, because this advancing is confusing.
okay, yeah, so So you set gain of 1, 0, 1 with probability half, and 0, 1, 0 with probability half, right? So this is the asymptotically optimal adversary for.
These are the experts still in descending order.
Right. So this is the leading expert, the middle expert, and the lagging expert. Right. So this is basically what I mean there. Right. This is how you set the gains. Again, this is much simpler than what one would expect. Okay, so that's the optimal regret and the optimal adversary. And here's the optimal algorithm. Again, you initialize psi to the same number, which, as you recall, is 1 minus square root 2 delta as delta goes to 0. It's square root of a characteristic polynomial. And the optimal algorithm is as follows. So you compute the cumulative gains for all the 3 experts. You compute the difference d1 between the gains of the first and the second. You compute the difference d2 between the gains of the first and the third, right? And you follow the lagging expert with this probability, which, as you can see again, is multiplicative weights algorithm on the lagging expert. And it's a further generalization now. So this probability mass is now split between these 2 guys to cancel. After that, it is again a multiplicative weights algorithm on the second lagging expert, and the remaining mass is put on the leading expert. Okay, and this again is the precisely optimal algorithm for every delta. Okay. Okay. So that's the story for 3 experts.
Psi is the same thing that.
Psi is the same psi for that. It's the same characteristic polynomial.
So it's about 1 minus root 2 delta.
It's, yeah. Psi is delta goes to 0. Psi is 1 minus square root 2 delta. Okay. So things get even more complicated for 4 experts. We don't derive the optimal algorithm, but we derive lower bounds on the optimal regret. And the techniques are again completely different from what we use for 2 and 3. The lower bounds are based on connections to random walks. And this is the regret we get. I'll specify the adversary strategy in a minute. And we very strongly believe that this is the asymptotically optimal regret. Okay, there's strong experimental evidence for this based on computer simulations. And if the conjecture is true, then this is also basically what the optimal algorithm can get by minimax. And therefore, the multiplicative weight algorithm is 32.8% larger than what you can get here. And the adversary which achieves this is again extremely simple. Okay, it's a generalization of what I wrote for 3. So it's 1, 0, 1, 0. Probability half, and 0, 1, 0, 1 with probability half. Okay. This is the adversary we study. We don't yet prove it is optimal. Don't think it's optimal. Okay. So we call this the comb adversary, right? So you could think of the way in which kids will divide into teams while they play a soccer match. The leading player will go to team 1, the second player will go to another team, the third player will go to this team, and so on. Okay, so that's the regret. So
Adversary is always advancing those 2 and those other 2.
yes,
So they will have the odd experts will have the same gain as the even experts.
No, because
No.
they.
no, because they'll swap, right?
It's changed.
They,
I mean,
the ordering.
The ordering, yeah, it's not the identities, yeah,
The ordering.
yeah.
And if there's a
Otherwise-
tie,
Otherwise, yeah,
Yeah,
yeah.
the order.
Okay, so I'll spend the next.
There was a question, what we do in a tie?
I guess it doesn't matter.
It doesn't matter, yeah. So I'll spend the next few minutes talking about how we compute the optimal adversary. Okay, so the most useful thing for computing the optimal adversary is that it is a weakly dominant strategy for the adversary to always be balanced. Okay, so what do we mean by balanced adversary? The expected gain for each expert can be the same. Okay, and this is irrespective of what is the cumulative gains that you gained so far. Okay, so you might expect that the optimal adversary is balanced overall, basically, but not just that. Even conditioned on what has happened so far, you still can afford to be balanced. That is, the probability mass you assign to each expert could still be the same. Okay, the optimal is always balanced, and the proof is very simple. Okay, suppose the optimal adversary were not balanced. Okay, then what is the best response algorithm for this optimal adversary? It will obviously go for the expert with the largest expected gain, right, which is larger than something else because it's not balanced. Now consider taking an arbitrary step at which this happens, right? The adversary is not balanced, and consider making it balanced. Okay, raise the expected gains of the other experts who are not equal to the leading expert. This does not help the algorithm because it already picked the. This does not help the player because it already picked the leading expert, but it could help the adversary because the max expert's gain can only increase by doing this, right? So there is no point not being balanced. Okay. And the biggest thing that we get out of this balanced adversary is that the algorithm is completely out of the picture now. Okay, while you analyze the optimal adversary, it doesn't matter what the algorithm does, right? The algorithm could blindly choose anything. Whatever be the algorithm, you get the same regret. And in particular, from now on, we are going to fix the algorithm to be uniformly randomly choosing an expert. Okay, you choose expert I with probability 1/k for each I, and therefore the regret, just expert minus algorithm is now max minus average quantity. That's it, right? So when you think of regret here, after it's max minus average, I'm going to use max minus average often. Okay, so
Clarify, this is not, you're not saying that this is the optimal algorithm.
Yes, this is not the optimal algorithm. If you fix, yeah.
So maybe say again why you're allowed to consider it.
Okay, so I mean, if the adversary is going to be uniform along all the experts, the algorithm doesn't care really which expert it's going to pick. So it could just throw a stone somewhere, and whatever expert it hits, you choose that expert, right? You get the same gain.
It's an equalizer.
Yeah. Of course, this is not the optimal algorithm, so I spent the slides talking about what the algorithm is. Okay. So.
Wait, go back.
All your other slides were about how you have these algorithms that do better than multiplicative weights, and the whole time I'm thinking, how can it possibly do better? Because what can you do against these adversaries? It's just doing something balanced. So I don't understand how this.
So this.
So I mean, we are doing minimax here. So if you fix the worst adversary, what you do as an algorithm, and if you fix the algorithm, what the worst adversary does for it. If you fix the multiplicative weights algorithm, I can design an adversary which will inflict some amount of regret on it. Okay, I can design a better algorithm where the best adversary designed for it can only inflict lesser regret. That's basically the point. Right? You give me the multiplicative weights algorithm. I design the adversary specifically for that algorithm and inflict some regret, and then use this algorithm.
So the one that inflicts this 47% extra regret isn't the one you told us, it's something else.
Yes.
Right.
Right, because minimax is an equilibrium, and equilibrium breaks if the algorithm is, the player is not following the optimal algorithm, right?
Actually, when you say that you are 47% better than multiplicative weights, do you know that this is tight? I mean, do you have a law?
Yes, so it's just what is known for analysis. I mean, we wanted to construct a counterexample. We have something, but not quite pin down the numbers. But yeah, that's
So all you can say for sure is 47% better than the best bound known.
But
right.
actually, there are lower bounds for multiplicative weights.
There are lower bounds for multiplicative weights, but those lower bounds are.
Oh, they are way up. Okay.
Yeah, because
In terms of,
I mean, the best lower bound I know is square root. log to the base 2, okay, but this is, the gap is larger, basically. So I mean, I said 47.5%, which is 1.47, and this is more like 2.35 gap, at least for k equals 2. So that lower bound doesn't help, so you have to do something else. But we try to do it, we have something, but it's not quite. Okay, so for the optimal adversary, which is a balanced adversary, while analyzing that adversary, you can forget the algorithm. Okay, that's the point I've made so far. So what does this balancedness give us, right? It immediately gives us what the optimal adversary is for the case of k equal to 2 experts. Why is that? So you look at the regret expression, which is the max minus average, which is just proved. Now for the case of k equal to 2, max minus average is simply the half of the absolute value, absolute difference, and you just split the cumulative gains, okay, and write this, right? Capital G is sum of little g's, right? Now consider this random variable xt, which is g1t minus g2t. Okay, what can this be, right? I said the gains are just 0 or 1, so g1t minus g2t could be either -1 or 0 or 1, right? If the adversary is balanced, what does that mean? The expectation of xt has to be 0, right? So what is the only choice left for you? The only choice left for you is what is the probability with which xt is equal to 0, right? So you are the guy who's designing the optimal adversary now, and these are the restrictions. Because of balancedness, you have these restrictions. The only choice in your hand is what probability you can set for xt to be 0, but the goal is to maximize the total distance. You have to have absolute distance from the origin, and if you want to maximize that, there is no point being lazy, right? There should not be any element of laziness in the random walk. So you basically have to design a simple random walk, right? You go right with probability half and left with probability half, which is precisely experts always disagreeing, right? Gain of 1, 0 with probability half, and 0, 1 with probability half.
There's no regret for the algorithm. Instead, you agree. So that's the proof.
Exactly. So what did we do so far? So the adversary's available actions are 1 or 2, or advancing expert 1 alone, or 2 alone, or both of them together, or none of them. And we said that there is no point being lazy and sitting at the same position, which means there is no point in advancing both of them, or no point in advancing none of them. The remaining is just 1 and 2, so you advance expert 1 alone with probability half, 2 alone with probability half, and this is the optimal adversary. Okay. So the simplification afforded for the k equal to 2 case doesn't carry over to k equal to 3 or larger. This max minus average business boiling down to half of the absolute difference doesn't go through. Things become way more complicated. So what do we really want, right? So the adversary's available actions are all subsets of 1 to k, just like adversary's actions here was 1, 2, 1, 2, 2 to the k actions. And you basically have to construct a balanced distribution at every single step, right, to maximize this max minus average quantity. Okay, so you're constructing a controlled random walk, so to say. So basically at every step you have a convex polytope of balanced distributions, and there are exponentially many vertices for this convex polytope. Okay, it's not just that the number of vertices of the convex polytope is exponentially many. Even if you have just 2 choices, it's still complicated because you have a number of steps. It's a controlled random walk that you have to design. Okay. So this is
exponential in 2 or 3.
Yes.
Exponentially in k.
Exponential in k, yeah. Okay, so I'll come back to deriving the really optimal adversary for 3 and 4 later. For now, I'll go to the optimal algorithm. So the optimal algorithm for the finite horizon model can be computed by backwards induction, right? It is going to be inevitably dependent on t, the number of remaining time steps, and therefore does not lend itself to succinct description like the other ones. You don't get any structural insight by deriving the optimal algorithm like this. You can derive it in time t to the k. It's good for small k, but there is this annoying dependence on the number of remaining time steps in t. Okay, so we'll move to the geometric horizon model, and from now on I'm going to talk about deriving the optimal adversary and the algorithm simultaneously. Okay, for 3. So, okay, even for 2 we haven't derived the optimal algorithm yet, right? I'll do that. So this max minus average quantity is translation invariant, because if you add a scalar to all the cumulative gains, nothing changes. Therefore, I can normalize the gain of the leading expert to be 0, right? The leading expert is at 0 always, and the lagging expert is at some x, which is negative. The optimal algorithm's probabilities are simply a function of x, right? Because it's simply a function of the cumulative gains. The cumulative gains here is just 0 and x, so it's just a function of x, p1 of x and p2 of x. And I'm going to use f of x to denote the regret to get starting at 0 x, this cumulative gains, okay? So what happens, right? If you start at 0 and x, adversary has 4 different actions. If the adversary decides to advance expert 1 alone, then from 0x you move to 1x, right? The cumulative gains will move to 1x. But 1x is not in our format, so 1x basically has to be smooth, normalized to 0x minus 1. You take 1 in both, nothing changes. And when you advance 2 alone, you go from 0x to 0x plus 1. When you advance both 1 and 2, 0x goes to 1 and x plus 1, right? Which again has to be brought back to 0 and x, subtracting 1. And when you advance nothing, 0x stays at 0x, right? So what does this mean for regret, right? So if you start at x, right, 0x, there's a probability delta with which the game will end then and there, in which case you will get a regret of 0 because the leading expert is at 0, right? The cumulative gain of the leading expert is 0, so max minus average will be 0. The max is 0, average didn't get any time to go, it didn't get any gain. With probability 1 minus delta, the game will proceed. So you'll get the max of these 4 actions. So I'm now looking at the adversary, which is the optimal adversary when the algorithm follows these probabilities p1 and p2, right? So what is optimal adversary? If it follows expert 1, right, then you go to the configuration 0x minus 1, in which case you get a regret of f of x minus 1, right? You start at x minus 1. But you should subtract p1 because p1 is what the algorithm gets, right? What is this plus 1 doing here? The plus 1 is for going from 1x to 0x minus 1. You subtracted this 1 and that will add to the regret, so you should add plus 1 there. And when you follow 2, the situation is that you are at x plus 1, so the regret is f of x plus 1 minus what the algorithm gets, which is p2, and if you follow 1, 2, then you go to 0x, so you should write f of x, but since you went from 1 to 0, there's a plus 1 here, there's a minus p1 minus p2, and then if you do nothing, you just stay at f of x.
Again, what f of x really means?
F of x really means the regret that the optimal adversary for the best response adversary for this algorithm p1 and p2 gets if you start from cumulative gains of 0 and x, right? 0 is the leading expert, x is the lagging expert, x is negative therefore. If you start there,
additional regret, not any, you ignore any accumulated regret from the.
Yes, that is why if you that's why here I say delta times 0. So if you stop right away, you get 0, right? Okay, so this is what it is, and you have to solve this recurrence. First of all, you can ignore these two guys, right? Why? Because 1 minus p1 minus p2 is just 0, because p1 plus p2 is 1. So these guys don't do anything, right? You're just staying at the same point. These are useless actions. So you just have these two, right? So you have a max of these two, but still max is pain to solve. How do you simplify this? Well, we know that the best response adversary for the optimal algorithm is the minimax optimal adversary, and we just derived the minimax optimal adversary to be this 50-50 adversary, right? And if the adversary is just a 50-50 adversary, it has to be indifferent between playing action 1 and playing action 2, and therefore you should be able to equate these two guys, right? So this should be equal to this, and that's what I'm doing here, right? The minimax optimal algorithm will make the minimax optimal adversary indifferent between the two actions it has at its disposal, which is advancing expert 1 alone or advancing expert 2 alone, right? And now since you have this, you can add this and divide by 2, which will eliminate probabilities completely, right? So you have this recurrence, and for good luck you also add the boundary condition, what you do at 0, which is slightly different. Now you have this complete system, and here comes the characteristic polynomial for this, right? It's x squared minus 2 or minus delta times x plus 1, and the roots of this polynomial are exactly the psi I talked about, And if you solve this, right, you get two roots I1 and
Go a little slower. How did you had f of 0 and f of minus 1? What?
so forget what we do at the boundary condition, right? I mean, let's forget that for now.
Okay, you want to?
Right, so let's forget that for now. Let's go over what we did here, right? So this is what we had here. So we had these 4 things and we threw away 2 useless things. And therefore now you have these 2 guys, right? Now there are 2 actions and the optimal algorithm is making the optimal adversary indifferent between these 2. And therefore I can equate the regret you get from these 2 guys.
Right. And then you got this recurrence.
And then we got this, and then we average, right? And that throws away the probabilities.
Okay.
So you just solve this, whatever you do to solve it, you get the probabilities out of it.
So the x there has nothing to do with the other x.
Okay, yeah. So,
maybe
so I should have used y or something here for the characteristic polynomials. I mean, this x has nothing to do with the x.
So this is in order to recurrence, so you know that the solutions are sums of some linear combination of 2 geometric.
Yeah, so let me just hide this. Now you just solve the recurrence and get these probabilities. That's all you should do.
So this is the second order, right? So you need 2 boundary conditions to get a completely discrimination. So
Why?
fx depends on fx minus 1 as well as fx plus 1.
Right, but the only boundary you get is at 0, right? Because, I mean, so when do these equations fail? These equations fail only when x is at 0, in which case this is 0 plus 1, 1. 0 comma 1 is a meaningless thing. It says that the leading expert is 0 and the trailing.
What was saying, in order to solve completely the recurrence, you need 2 boundary conditions, otherwise you still have some free parameter. The next.
Right. Okay, it is true. Okay, so you get 2 constants, C1 and C2, and one of these constants has to be 0, otherwise the regret will go to infinity. Okay, so the solution can be one of these constants has to be 0. If not, the regret will go to infinity, and because of that, you can eliminate that. You use that to eliminate that, and the other constant can be derived using the boundary condition, which is.
Because the other solution of the recurrence is larger than 1.
Right. Okay, cool. Thanks. Okay, so this is the probability with which you play the leading expert. This is the probability you play the trailing expert. So what happens for k equal to 3? Well, you have 8 actions. So you write the max over all these things. Now what do you do, right? For k equals to 2, you had the knowledge of what the optimal adversary is, and therefore you said that I'll go and equate the regret you got for these 2 actions. For k equal to 3, you don't know, it's much more complicated. So we wrote programs to see that the optimal adversary was always doing either 1 or 2, 3, or 1, 3 or 2. Okay, so both were optimal. So you just advance 1 and 3 together, and then 2 separately with probability half, or 1 with probability half and 2 and 3 separately with probability half. Both were optimal. Okay, most of the time that was what the optimal adversary was doing. Therefore, you just want to do a guess and verify strategy here, right? You know that this is optimal, you guess that this is optimal, so you just equate the regret you get out of these 4 guys, and this is purely out of simulations, right? This is where the optimal adversary is helping you do this. And after equating this and writing all the boundary conditions, what happens when x1 equal to x2 and so on, and then getting pain for 4 or 5 hours, finally you verify that the strategy you get by equating these 2 guys indeed satisfies the max equation, and therefore what you got, the guess you made was really correct, and that also will give you the optimal algorithm out. Okay, you can solve for the probabilities.
It doesn't seem to scale very well.
Cool, yeah.
So for 4, do you know anything?
No, for 4, at least for 3, this is optimal. For 4, it is starting to get delta dependent, the optimal adversary, so it becomes complicated. So for 3, the optimal adversary is not delta dependent. For 4, it's slightly delta dependent, but asymptotically it is not delta dependent. Right? As delta goes to 0, it is the comb adversary 1, 3 or 2, 4.
But it seems
It no for 4 it seems it seems to be asymptotically optimal, right? Well, at this point I don't have any doubts at all that it is the asymptotically optimal. It's just a question of proving. So.
But can you prove that it is delta dependent for 4?
Yeah, by simulations basically. I mean, yeah. Okay, so this is what we get for k equals 3. So what's the optimal adversary? There are two optimal adversaries, like I said. Either it is 1 or 2, 3, or 1, 3 and 2. Okay. So, but this is what we call the comb adversary, right? Because it's 1 and 3 and 2 in between, right? That's what generalizes easily. So, what's the optimal adversary for gentle k? This is the conjecture, right? If you prove this, it'll be cool. Basically, the optimal adversary we conjecture as delta goes to 0 is simply this. You advance all the odd experts with probability half, all the even experts with probability half. Okay. So this generalizes the optimal adversaries for k equals 2 and 3, and this is again supported by computer simulations even for 5. And
this might still be optimal for fixed horizon as t goes to infinity.
yes. Mm-hmm. Yeah. 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 I mean, at the end, while you get very close to t, the adversary will start behaving crazy, but for most of the time steps, it will be this, right? Because that is where we got all this insight from. We wrote all the programs for the finite horizon. And for the finite horizon, we could see the comb adversary for k equal to 3, for instance.
So does it follow any pattern for k large k? Does it goes to like MWA or something like that?
What goes to MWA?
The optimal adversary.
I mean, it seems to be this.
It seems to be the comb adversary. This is.
So if your conjecture is right, how quickly does multiplicative weights become optimal as k goes up to infinity?
Yeah, we don't know how to calculate the regret, right? You have to calculate the regret for this guy. That itself is a challenge. So I'll say how to do it for k equal to 4, 1, 3 and 2, 4, and then you'll see why it's a fight.
So each time you increase k by 1, you kind of square the amount of work you have to do.
That's why that's not scalable.
Yeah, but that's a good point. I mean, if you can just compute the optimal regret, or the regret for this particular strategy, that itself will be something. Okay. So, what is the connection between finite and geometric horizons? Right? You have all these results for geometric horizon. Can you port them back to the finite model? So, how are RT and R delta related? So, the obvious point is that the regret you get in the delta model, R delta, is smaller than this infinite series, right? Because if I tell you in the delta model that after drawing the time that this is the optimal t, then you can do something. But in the delta model, you don't know it. Therefore, you can't get any better than what you can perform if I tell you the t. So one direction is obvious, but the conjecture is that as delta goes to 0, it's basically the same. Okay, the adversary does not benefit out of getting informed about the t which is drawn from this geometric distribution. Okay, and again for k equal to 2, this is true not just asymptotically but for all delta, because for k equal to 2, the optimal adversary didn't care about the number of remaining time steps. It was just independent of t and delta and everything. Therefore, for k equal to 2, this delta t theorem is not just a conjecture, it's a theorem, and that too for all delta. But even for larger k, we believe that this is true, and again this is supported by simulations.
The smaller the delta, the more information you're giving me. Because the distribution is more spread out. So even though, so somehow, okay, it's interesting.
That these two are,
Right.
as delta goes to 0, that they should converge. But this does happen.
Right, so you give me more information, but it doesn't matter more. Because
It doesn't matter more.
because what's happening. I understand. Yeah.
Yeah, it's exactly this story of the, the sun will swallow the earth. Is it 6 billion years or 12 billion years?
So what if this were true, right? If this were true, then we know how to tackle the geometric horizon model. And if you have R delta, which you compute with the geometric horizon model, you can just immediately read off RT from this by multiplying by square root of pi over 2. This again I believe is true. Okay. So I'll now go to regret lower bounds, right? Basically going to compute what the comb adversary does for k equal to 4, right? The 1, 3, 2, 4 strategy which I wrote there. So recall that this is the conjecture strategy for 4. So just get a feel for what happens, right? If you have 4 experts, if you advance 2 and 4 together, this is what happens. If you advance once more, they coincide. If you advance 2 and 4 once more, 2 gets ahead of 1 and 4 gets ahead of 3, which is meaningless, and therefore you have to swap, right? Therefore you get to this configuration, right? Now if you think about this, if you stare at this for a few minutes, you'll immediately realize that the distance between 1 and 3 will be the same as the distance between 2 and 4, okay, in this advancing process. And therefore to keep track of the 4 experts, it's not necessary to keep track of all the 4, you can just drop the 4th one. So we're going to keep track of the 1st, 2nd and 3rd, because that will tell you where the 4th expert also is. And now, because this process is translation invariant, I'm going to map it to another process which will maintain the relative distances between the 2 experts. So advancing 1 and 3 and 2 and 4 doing this strategy is equal to the following random walk of a particle between a reflecting wall which is fixed and doesn't move and another wall which moves, okay. So let's say this is the fat fixed wall which reflects and this is the wall which moves. So this ball moves to the right or left with probability half. If it moves to the right here, it sits at where the wall is. If it tries to move one more step to the right, it will get bounced back, right? If it moves to the left, it keeps moving to the left, it will coincide. But if it tries to move one more step to the left, it will stay at the same point, but the wall will move, okay? So this side is a fixed wall, and that side is a movable wall, okay? And this, you can, if you think about it for a few minutes, maps to the 1, 3, 2, 4 adversary, right? Adversary 2 moving is like this ball moving one step forward. Expert 2 and 4 moving is like the ball moving one step forward. Experts 1 and 3 moving is like the ball moving one step backwards, right? Now what do you want to compute for this random walk? Well, you want to compute the max minus average, and this max minus average is a quantity which doesn't change. It increases in expectation by half exactly when the wall 1, this fixed wall, and that particle coincides, okay? Only when there is a swap something happens, okay? So what you need to do is compute the expected number of visits of this particle. I'm saying particle 2, it's not that there are 2 particles, but just to say it maps to 2. P2 to W1, right? This is what you need to compute. And again, this is translation invariant. I'm going to fix the wall 1 at 0, and let's say W3 is at negative L, right? So what you need to compute is, separation of the 2 walls going from L to infinity, the sum of the expected number of visits of P2 to W1 when W3 is at minus L, right? If you sum over all these things, you get the total expected number of visits. So V12 of L is basically the expected number of visits when the wall 2 is at minus L, right? Sorry, wall 3. There are only 2 walls, but when I say wall 3, I mean the 3rd one, right? So when that is at minus L, what is the number of visits? And that is product of 3 quantities. So I'm going to set theta to square root 2 delta as delta goes to 0. This I won't derive, but I'll just explain what it is. So Q1 of L is, first of all, the wall 3 has to reach minus L, if at all you want any visits when W3 is at minus L. So what's the probability that it reaches minus L? And then there's a question of the particle 2, basically after pushing the wall, is very close to the wall.
Delta, we stop the whole exercise. So that's why W3 might never reach
minus L. And the second thing is, you're talking about the number of visits of P2 to W1. For that, first of all, the particle P2 should first reach 0. That's where W1 is, right? It should reach before reaching minus L minus 1, right? Which before pushing the wall, it means. That should happen. And after that, there's a question of the number of visits of P2 to 0 before the wall moves one step further, right? So I'm not going to derive all these things, but this probably is familiar, right? When P2 is at minus L plus 1, the wall is at 0, You are at minus L plus 1. This is the particle. And there is the movable wall, W3, at minus L, right? What's the probability that you reach 0 before you reach this guy, right? So if there are no stopping, it's basically 2 over L plus 1. With stopping, it's sinh 2 over sinh L plus 1. Okay. If there is no stopping, it's 2 over L plus 1. Okay, so I'm not going to derive these other guys, but you have all these things. So if you multiply all these things, you get 1 over cos cubed L theta. And what you need to do is sum this guy from L equals 0 to infinity, and this is the same as the integral. If you integrate this, you get the beautiful pi over 4 outside. So the constant in front of 1 over square root 2 delta goes as k equal to 2, it is half, k equal to 3, it's 2/3, for k equal to 4, it is pi over 4. Okay. Then go to your computer and pray that this is basically matches what your simulation says. You get RT out of simulations, you get R delta out of this, right? You divide this, you get exactly square root pi over 2, which is what you want, right? So this basically tells me that this is the optimal adversary. It's only a question of proving. Okay.
You can actually simulate RT.
I can simulate RT for small t, right? I mean, it's
Yeah.
you can,
For which t?
till t equals 3, even 4. Oh, sorry, t. I mean, for t, that depends on k, right? For k equal to 3, I can go till 300 or 400. For k equal to 4, even lesser. So.
For k equals 4, what is t? What did you say?
Sorry.
When k is equal to 4.
What t can we do?
Yeah.
About 100 to 120. And that already says this. Basically, I mean, we got this constant pi over 4 before we derived this. I mean, based on simulations, and we had 1 or 2 attempts before getting this pi over 4. We didn't know what this number was. 0.78 we got. And pi over 4 is exactly that. So.
We didn't have enough precision to plug into the
Yeah.
zone. The pi over 4, people should just recognize.
Yeah, Mickey would recognize it.
Yeah. So this is the evidence for optimality of the comb adversary. So just go prove it for general K. That's the open question from this talk. Thanks for listening. That's it.
Any other questions or comments? Yes.
So I'm just curious about this computational complexity of this. So what I'm wondering is, let's say that we settle for something less than towards optimality or whatever.
Okay.
So from the discussion, but the overall intuition I get is like, since you know that the adversary is following, the optimal adversary is following some kind of balanced distribution. So why can't, I mean, a simple strategy would be, so for k greater than 3 or 4, so in that case you could do like choose first. So at any time step you know in the order like which one is leading, second, third, and you know this whole thing.
Sure.
So choose first. So take any let.
Go ahead.
So you are taking the arms, right? So I'll say that you choose first 4, 7, second, 5th, 8th, and third, 6th, 9th. So I just go in this order. I can do that, right? I can form these 3 subsets of these arms. So let's say that you had.
But the strategy is suggested as a conjecture is even simpler, right? It just advances.
But it's
Are you
not
talking about
tractable.
For
It's
the
not
player,
tractable.
are you talking about for the player or for the adversary?
I am for the player.
I was talking for the player.
Okay, for the player, what are you suggesting as the
Let's say that you choose first.
at a given gains configuration? What will you do?
Choose 1, 4, 7, 10, and so on. You have the solution for let's say 3. For
What does it mean to choose all of 1, 4, 7, and 10 equally likely, or
you want to advance equally likely, let's say.
Oh, that's what advancing them is what the adversary does.
I mean, you have to pick, right?
Maybe this question is best discussed kind of offline. So
Okay. Yeah,
maybe
probably
we'll,
I'll discuss
stop.
offline this.
Stop here. Balu is certainly available for questions, and thank you again.